Alright, hi guys. My name is Milo. This is Hyejun, and that is Ari. And if you guys were ever wondering about like how maybe your phones, laptops, or like modern day electronics work, even though they're so small, like how they work so fast, how they can store so much information, we're hoping to kind of like let you understand a little bit more. So what lets this all happen is photolithography, and that is the process by which you microfabricate a pattern on a thin film or a bulk of a substrate. And because you have to be really precise when you're going for really tiny circuits, so you have to go to like the nanometer range. And with photolithography, that's possible. And that's our image we're going for, I guess.
Yeah.
It's on to you.
So I guess it's my turn. Obviously we didn't like make like the Intel sized computer chip photolithography circuits, but we did a much bigger version in the lab, and so this is the analogy sort of that shows it. The first sort of base layer of when you're doing photolithography is a substrate, which you can just think of like a just anything that everything goes on top of, kind of like a base. And then on top of that, you put whatever metal you want to be doing putting a pattern on, which in this analogy is the grass. And then really the first step in photolithography is to put this layer on top of the metal, which we like to call a photoresist. And really that's just kind of this material that when light hits it becomes soluble in water, or actually not water, what's called the developer solution. And so that photoresist is represented by the snow here, and was being coated by the snowing clouds. The next step is masking. And so they kind of did two steps in one here, but these clouds here are preventing the light from reaching these two these two patches of snow, and that kind of leads me to exposure, which is when we shine light on the wafer, and the parts that aren't covered by this mask, or in this case the clouds, get exposed and are washed away by the developer solution. But in here, because it's snow, it just kind of melts away. And then the next step in the process is etching. So this is sort of represented by these lawnmower corporation little guys. But basically, the etch solution gets rid of all the metal where it's not covered by the photoresist. And so in this case, the lawnmowers obviously can't mow over these huge patches of snow, so everything else goes away. And then in the end, you're left with no grass in the areas. And then obviously, they didn't show it here, but the final step would be to remove this snow, and you'd have little patches of grass here and here. And there's that's sort of the process. And there's one other big idea that this analogy is trying to show. I don't know if you guys can see it clearly from your point, but there's this dialogue that says no more gas. And again, here you can see this little patch because he didn't have enough gas. That sort of speaks to like a theme in photolithography. As you get smaller and smaller and smaller, and you're trying to make smaller things and everything gets closer together, the holes in your mask, so that would be the distance between between this cloud and this cloud, sorry, the laser pointer is getting a little small, becomes so small that they start to mess with the light and you're not able to accurately expose. And so what we need to do is, you don't normally think of light as having sort of like a size, but in the nano world, everything is so small it really does matter. And so by the higher energy light has, actually the smaller it is, it has a smaller wavelength. And so the more gas sort of correlates to we need more power to make a beam of light with more power, and so you can get small enough to really be accurate and really get everything you want to get. And so that's why that grass, that little patch is there, and if they had more power, they would have been able to get rid of that.
So actually, the illustration showed positive photoresist, and so a limitation was that they didn't show negative photoresist, which is when the light strengthens the metal instead of weakening it. And as feature size decreases, it becomes harder to control resolution. And so Gordon Moore is the creator of Intel as well as an engineer, and he created this prediction that known as Moore's law that predicts every 2 years the size of transistor halves, and in turn they double in efficiency and speed, which means, but they also get increased resistance in the transistors. So it is important to find a material with low resistivity, which is how easy it is for electrons to pass through a material, whereas resistance also takes into account size and shape of a material. So high resistance can lead to energy lost as heat. And so one of the things we need to make like a photolithography, like to do photolithography effectively, is a clean room for semiconductor manufacturing and photolithography, because we don't want other light waves and dust to interfere with our experiment, because usually photolithography is like done at a very small scale, so even dust could like really ruin your experiment. So that's why we did a larger scale photolithography experiment instead. And so thank you.
Yeah. Any questions?
What was the metal you used?
All right, so we actually used copper, right?
Yeah.
And then at the bottom of it was substrate.
So often in clean rooms, they have kind of orangish, reddish light. Can you explain why they would use that versus, white light that we have in our rooms regularly?
Sure. So once the photoresist layer is coated, is put on, you want to have no light exposure, because that's going to start to eat away at that photoresist. And you don't want to have any exposure until you have your mask on and everything's really set up. And when we went to the clean room, they were telling us that orange light is much less destructive to that photoresist, because it's on, because again, orange light is on a longer wavelength, and so it basically has less energy, and so it's like less destructive to that photoresist.
Can I leave this mic with you, Andrew, so that I don't run around? Other questions? All right, so I have a question. So you mentioned positive and negative photoresist. Can you elaborate on how those actually function differently? Like what makes a resist positive versus negative?
So positive is you use the light to strengthen the metal, and for negative photoresist is you use the light to strengthen the metal, so that like the metal that wasn't covered with light is the one that you chip away. But positive photoresist is when the light actually weakens the metal instead. So that is the part that you lose.
Strengthens or weakens the metal?
Or the photoresist?
The photoresist,
Yeah.
right? So how would it, in the negative photoresist version, how would the light strengthen it? What is it actually doing to the resist? Do you know?
I'm not too sure.
Basically, the photoresist in that case is made up of a lot of single sort of strands of plastic or something like that. And when you apply light, it sort of bonds them into this polymer, which is much harder to wash away.
And then in the positive photoresist, what is it doing then? By contrast?
I believe in the positive photoresist, it's weakening the molecule somehow to allow it to be washed away. I'm not 100% sure about that.
Yeah,
Sorry.
it's just breaking bonds, right?
Mhm.
So in a negative photoresist, you're cross-linking the polymer, so you're taking all these different strands of resist and linking them together to make them even stronger, so that they're insoluble. And then in the positive photoresist, by contrast, you're breaking the developer, the photoresist down, so that when the developer comes in, it's soluble and it can take it away.
When might you use negative or positive method? What's the use case?
It really depends on like what you're trying to do. Different applications. Photolithography is used for like a lot of different purposes, and there's so many different applications. But it would have to be like on a case-to-case basis. Just different ways of doing things.
All right, thank you. Good job. Okay, one quick question. Go ahead.
With lithography, they use 4 different color negatives. Cyan, black, same like you see in your laser printer at home, or color printer at home. Would the number of filters, if you will, affect the number of negative, positive, all that? Would have an impact on it? I'm not sure.
I'm sorry.
Well, the thing Because
Are you-
lithography uses 4 primary negatives when you're doing lithography.
Oh, like on your printer at home with the.
Well, the printer's in the modern version.
Okay.
The original version was actual film with negatives. You have 4 separate negatives that you would use to filter the light through.
Oh,
and to
so sorry.
develop.
I think I get what you're saying.
Yeah.
Lithography is just sort of like a blanket term that we use to describe when you have sort of like one mold, like almost like a stamp, as a form of lithography, and you can stamp that a bunch of times. And so there's different ways you do lithography for different things. For instance, this way for nanoparticles, a stamp, or in printing, it's a little bit different, but it's still this whole same general concept.
Okay, thank you guys.